In this video, we introduce different graphs or distributions of our data. In particular, we're going to introduce the gold standard of distributions called the normal curve or the bell-shaped curve. Let's get started. So let's first go over some basic types of distributions that are pretty popular in statistics. The first two on the top of your slide here are what we call distributions which are skewed in one direction. So first, you notice here in the first one on the left here that most of your classes are heavily occurring on the right side of the graph. Whereas on the second one here, most of our distributions are occurring on the left side of the graph. Thus, we would say in the first case that we are skewed to the right, whereas in the second case, we are skewed to the left. So that's a skewed distribution. Okay, so that is pretty common, especially when there are things that over time are increasing or decreasing in a certain way. But there is a buildup, notice here. We have a buildup and then we have a fall. And in this case, we have a buildup and then we have a fall. Okay, so it's not simply a purely increasing like we have here at the end, purely increasing or purely decreasing without a buildup, right? So that is a little bit of a difference. So we have skewed distributions here. We also have something called a uniform distribution. Very rare and kind of boring, to be honest, but a uniform distribution is one in which the frequency for every single class is the same. They're all equally as likely to happen. So for example, if I gave a test and I had 10 students who got an A, 10 students who got a B, 10 students who got a C, 10 students who got a D, 10 students who got an F, that would be a uniform distribution because every class of grades had the same frequency, okay? And the helpfulness of a uniform distribution is that its appearance appears to be something like a rectangle, which means if we were calculating the area for each of the different classes or the percentage, it would be really easy using your length and your width for the rectangle. Okay, so it's very nice and uniform that way. But again, highly boring, if you will, and highly unlikely. Now, another type of distribution that we run across sometimes is called the bimodal distribution when we're looking at a visual representation in the histogram here. So what we mean by bimodal, remember, is typically you have two modal classes, right? Two modal classes. So when we thought about a modal class back in one of our earlier videos in the statistics unit, we mentioned that that would be the class with the highest frequency. And so here it looks like, well, this is your mode right here. This is your modal class, I would say. It's the class with the highest frequency. But in the case of the histogram, when you're trying to consider what a bimodal distribution would look like, you would expect to have multiple, or in this case, because it's bi, two different peaks, if you will. And so we see that happening here, like a peak and then a drop, and another peak and then a drop, okay? So when you have two peaks and not just the one peak like you do in those cases or in these cases, right? When you have two peaks in your histogram, we consider this bimodal, okay? So that's a bimodal. Now, technically, I know we remember that mode meant the most, so you're expecting there to almost be like a tie here, that they're the exact same height. But when we're talking about the visual representation of your histogram, this is what would be a clue that we have something called a bimodal distribution, so two peaks, not just one. Now, the last type of graphs that are on this slide for us to consider are what we call J-shaped distributions. Now, you might be wondering, why do we call it J-shaped? Well, the basic idea here is that they are constantly increasing or decreasing. No wind up, no wind down like we had at the first case. So in this case, something like this is looking like a J or a backwards J if you do it symmetrically. Okay, that's what we mean by J-shaped. Okay, so it's kind of a silly reason for calling it J-shaped in my opinion, but that is the reasoning behind it. It sort of looks like a J if you were to draw your line on top of the bars, or your curve, I should say. So again, the main thing with J-shaped distributions, you're constantly increasing or you're constantly decreasing. Okay, so those are all different types of popular distributions that you may come across when you're looking at data or people's presentations of their data. But the golden standard for data in the form of histograms or distributions is going to be the normal distribution. So let's take a look at our next slide. So the ideal distribution, or the gold standard, if you will, is what we call the normal distribution. Now, that's not to say that every other distribution is abnormal. It's just that we would prefer to have normalized distributions because it makes our calculations and our extrapolations, right, from a sample into a population. When you get to statistics, you'll understand more about that. It makes it a lot more uniform. It provides a lot of uniformity and a lot of easier calculations that we can depend upon. There's a lot of important information that's been studied about normal distributions that gives us the ability to make predictions about things. So we really prefer to have a normal distribution. And the high level of symmetry is also quite nice. So you notice what I mean by symmetry here. You have a bar in the middle. So this bar in the middle would definitely be your modal class, okay? And then you have symmetry on all of the bars left and right of it. So it's quite nice degree of symmetry here on both sides of your center, okay? And then if you were to draw your curve that is connecting the tip tops on the left, the top left corner of each bar here, and then on the other side, the right corner of each bar, you would end up getting what we call a normal or bell-shaped curve, okay? Now again, when you get into a formal statistics class, sometimes you have to approximate a bell-shaped distribution. So sometimes it's not perfectly normal, but it's going to be somewhat forced into that situation with a couple of parameters changed. So it's not always perfect. Sometimes you'll get something that's a little bit less perfect, right? So you can have more of a smushed down bar bell curve graph rather than a nice high bell curve graph. And so again, we'll talk about that in a statistics class. But the main thing to notice is that you do have what we call a bell-shaped distribution or a bell-shaped curve. You have a high degree of symmetry, and in particular, we have symmetry about the mean. So what does that mean? No pun intended. Remember, the mean is your average, so the average of all of your values is going to lie in the center of your graph. So this modal class actually would contain the average. If this was test scores, that average test score would be living in that modal class, okay? So that is going to be the mean. And if we're talking about a sample in particular, a sample mean from our sample data, X bar is our statistic that we use there. So what else do we know? Well, we know that the mean, X bar, the median, so the middle value of your data, the mode, or the most popular value, they're all going to be the same exact number if this is a perfectly normal distribution. And again, there are some distributions that appear normal at first to the naked eye, but once you do further examination, they're not perfectly normal, and in statistics we have ways of dealing with that. But if you do have a perfectly normal distribution of data, then we would know that the mean, the median, and the mode all have the exact same value, and that value would be right in the center of your curve, right in the center, okay? So you can have left and right. Left would be telling us, or the reader, it would be telling the reader values which are below the mean, right, that are lower than the mean, and to the right of the center would be telling you values which are above the mean, okay? So there are some things that have already been proven statistically over time to be always bell-shaped, okay? These are like absolutes that you can depend upon, and that would be IQ scores of populations. Believe it or not, IQ scores of various populations always come out to be bell-shaped, okay? Similarly, the heights of people always come out to be bell-shaped. Cholesterol levels, you wouldn't think that something like this would be so normalized, but in fact it is. It is going to be bell-shaped, okay? So we'll see some of these pop up in our examples in a moment, but keep in mind that is what we mean by a bell-shaped curve. Again, a nice bell shape with high degree of symmetry about the mean, and that the mean, the median, the mode are all going to have the same value, and they lie in the center of that bell curve. Okay, well, let's continue our discussion with this first example and see if we can put that idea into practice. So here we're talking about something that is normally distributed, and that would be IQ scores. So we're told that IQ scores are normally distributed, and that the average IQ score is known to be 100. Now again, typically we would use X bar for talking about a sample mean, X bar for a sample mean, or we would use mu. We talked about that in a previous video. That's a Greek letter that is used for the population mean. So typically this would actually be mu, because this would be talking about the population of all IQs. But suppose we just are talking about a sample in this case, since that's all we've described so far in this class. Then what they've given me so far is my mean, okay? Assuming this is just from a sample of IQ scores, but even though we know in reality this is the entire population. It's also known that the standard deviation is 15 points, okay? So IQ is measured in points, so 100 points is the average, and 15 points is the standard deviation. So assuming this is from a sample rather than a population, we would use S for standard deviation. So S is 15. So these are the givens, okay? And anytime you're approaching a math problem, especially as you go into statistics, you always want to write down what you know and what you want to know, and then figure out how to use that information to answer the question. It says, how many standard deviations away from the mean are the following IQ scores, okay? So again, because they told us already that this was a bell-shaped distribution when we're talking about IQ scores, it is perfectly reasonable to draw a bell-shaped graph. In fact, if you're highly visual, and even if you're not, I encourage it just to get used to the ideas here. You should go ahead and draw yourself a bell-shaped curve anytime you see the words normally distributed, okay? What else do we know about normally distributed graphs? Well, you have a high degree of symmetry, they're bell-shaped, and they are symmetric about the mean. So that means the mean is in the middle. So x bar equals 100 should be in the middle. Okay, so that would be represented in that location right there. Technically, there's a modal class right there, but we'll continue. So now they pick a particular score for us to consider. They would like us to consider this score of 85. Now, where would that be in this normal distribution? Would this be above the mean or below the mean? Well, it's less than 100, isn't it? So it would definitely be below the mean or to the left of 100. Now we're told that the standard deviation is 15. So if we were to walk, right, 15 to the left, what is 100 minus 15? Well, that's 85. And if we walked another 15 to the left, what's that? 85 minus 15 is 70. And you can continue this idea. Walk another 15 to the left and you're at 55, right? And you could have also walked 15 to the right. You would have been at 115, 130, another 15, or 145. Now, the beauty of having a normal distribution is that if you go one standard deviation to the left or to the right, they should represent the same percentage under the curve because of the symmetry, okay? So let's take a look at what this is saying here. They want us to know they want us to tell them how many standard deviations away from the mean is the score 85. Can you see that right now? Where is 85 located? It's located right here. How many standard deviations is that below the mean? Just one. So this would be one standard deviation, I'm going to use DEV for my abbreviation, below the mean. Now that has significance to us. We're going to talk about what the significance of one standard deviation below the mean means in a moment. Typically, if you were doing a statistics class, you would learn the concept of what we call a z-score, which is a way of normalizing any raw data, comparing it to the mean and the standard deviation, and to come out with a number. That number of the z-score tells you how far you are from the mean. So if we were doing that calculation, it would be x, so that's 85, minus your mean, 100, divided by your standard deviation, 15. You would end up getting -1. And that makes sense because you are one standard deviation below the mean. And the reason that formula will become important in statistics, if you've already taken statistics, you already know what I'm talking about. It tells you where to look if you're looking at a table of values, exactly where to find the probability above or below that number, okay? So for now, all we want to know is conceptually, do you understand how many standard deviations this value would be from the mean? Yes, one standard deviation below. Great. Then with that information, pause the video and try the second one on your own. Okay, let's see how you did. Because it was normally distributed, hopefully you drew a nice bell-shaped curve. Hopefully you remembered that in the middle of your graph is the mean, which is 100 for IQ scores. And that if you go standard deviations of 15, you would have what we had above. You'd have 85 to the left, then 70, and then 55. You would have 115, 130, 145. Okay. So when we're asked to compare 130 here, what do we see? 130. That's right, 130 is 2 standard deviations above the mean. 115 would be 1 standard deviation above, but 130 is another standard deviation. Thus, the answer is 2 standard deviations above the mean. Again, below and above is important, but for now they just asked how many. So 1 is the first answer and 2 is the second answer. And if you were using a z-score formula, the first one would be z equals -1 since it's 1 below, and the second one would be z equals +2, which is 2 above. Okay, let's head over to our next slide where we put together this idea of a normal distribution and the number of standard deviations that you are from the mean. And this idea is called the empirical rule. Sometimes we refer to it as the range rule of thumb, or the 68, 95, 99.7 rule. There's different names, but for our textbook, we're going to go with the empirical rule. So what do we mean by the empirical rule for normal distributions? Well, first of all, this rule only works if you have a truly bell-shaped graph. So if it's not normal, it doesn't work. So that's really important. Secondly, The basic idea is that if you were to divide this under the curve into different regions, you have a guarantee of a certain percentage of your data or of your population or your sample set in this case must be in that space. So the first thing we want to notice here is that there's a lot of symmetry going on. So our mean is in the middle, there's our X bar, and we're told that 34% are here and 34% are here. Nice and symmetrical. Well, what would happen if you added 34 plus 34? You would get 68. And that's what the first part of the empirical rule says for a normal distribution. It says that 68% of all data must lie within or between one standard deviation of the mean. So if you go out, this is like our z of -1, right? If you go out one below or one above, one standard deviation in either direction, you would have 68% of all of your values there, okay? So that's the first thing we notice. The next thing we notice is if we go out 2 standard deviations, so -2, that represents 2 below, or +2, that represents 2 above, we are noticing the numbers 13.5 and 13.5, another high degree of symmetry. What happens if you add those two numbers together? Don't you get 27? Is that right? Did I add that right? Yes, 27%. And what happens if you add that? So that's 27% between the two of these. We already had 68%. So what happens if you add 68, what we already had, plus the 27 that we now have? What do we get? That's right, we get 95%. So it turns out that 95% of all data, this is real important, 95% of all your data will always lie within 2 standard deviations of the mean. So if you're talking about an IQ score, or if you're talking about an SAT score or a cholesterol value for data that is normally distributed, and you know that this particular IQ score, let's say, is 3 standard deviations above the mean, well, that's very unlikely, since 95% of all of your data has to be between 2 standard deviations of the mean. Okay, only 5% is left for the outside there. So that is incredibly important to notice. Now, the last thing we're going to memorize in our little form here is what happens within 3 standard deviations of the mean. So notice we have these numbers, 2.35, 2.35. Some textbooks will be a little bit not as accurate here, but we're going to try to be very, very careful here. If you add 2.35 and 2.35, you end up getting what? That's right, 4.7. And if you add 4.7 to what we already have here, we've already talked about 95% of all data, what do we end up getting? That's right, we get 99.7%, which is telling us that 99.7% of all values must lie within 3 standard deviations of the mean. So technically, could you be beyond 3 standard deviations of the mean? Yes, but you'd be in that 0.3% of the population. So very unlikely. So if someone tells you that their IQ score is a certain number and you calculate that that's 3.2 standard deviations above the mean, they may not be being honest with you, just saying. Okay. So you do need to memorize this. 68, 95, 99.7. It's going to be coming in handy quite a bit, and you'll see in our next example how we can apply this. So when you're ready, move on with me. Here comes our last example. It says, assuming that you have an SAT math score, and you're told that they are normally distributed with an average or a mean of 500 and a standard deviation of 100. So they're giving you the mean. Notice every problem is kind of similar here. They're giving you the mean, or X bar if it's from a sample. Now again, technically this is from a population, but for the purposes of our class, we'll stick to sample. So the sample mean here is 500, and the standard deviation S would be 100. So what are we told here? Well, they would like us to find the percentage of students who earned the following SAT scores for math. And again, it is important that they tell us that it's SAT math, because it turns out SAT math is different than SAT English, not only in the content, but in how often people score certain scores, right? Usually the SAT math scores are going to have lower averages, right, than SAT English or verbal scores. That's typically what happens, at least in my experience for a lot of years here. So when we're talking about the mean for the math of 500 and a standard deviation of 100, that should inform us as to how to answer this question. So let's start with the first one. We'll do it together, and then I'll see if you can try 1 or 2 of them on your own. Because they tell us that this is a normal distribution, the first thing I should do to visualize things is draw that bell-shaped curve with a high degree of symmetry about the mean, right? So the mean goes right in the middle, and they told me that the mean is 500. Now they also told me that the standard deviation is 100. So one standard deviation below the mean would be represented by 400, and above the mean would be represented by 600. Two standard deviations below would be another 100 that I subtract. So I'd be down at 300 here, but adding 100 the other direction, you'd be at 700. And if I subtract another 100 from the 300 that I started with here, I'd be at 200. And again, adding 100 to 700, we're at 800 here. Okay, and in fact, I'm going to go ahead and do that for all of these real quick. Feel free to pause the video and do that yourself, because these are all going to have the same general information, same situation, right? SAT math scores of mean of 500 in each case. Should have copied and pasted, that would be faster for you, but hopefully this gives you time to do it as well. All right, so then you notice because it's a standard deviation, you're going to have your same numbers as before, 400, 300, 200. Below and above we have 600, 700, 800. Same thing here, 200, 300, 400, and then above is 600, 700, and 800. Okay, once you have your setup, let's see if we can answer the first question together, unless you want to do it yourself, which is definitely encouraged. So the first question is, what is the percentage? Now again, I don't think I made this very clear, so I want to make sure I do. Under the curve represents all possibilities. So technically the area or the total percentage under the curve possible is 100%, or if you're talking about as a number, 1, right? And then decimals below 1 would be portions of the graph. So when we're talking about percentages, you can either talk in terms of 68% like we did on the last slide, or you could say 0.68 if you're using decimals and whole numbers. Okay, so when we're talking about the percentage of people who would score an SAT math score between 400 and 600, and maybe this is you. Maybe you look back at your SAT scores and you're like, I scored a 550. All right, so you'd be in this group. How likely was it that you would be in this group? Let's take a look. So 400 lives here, one standard deviation below the mean. 600 lives here, which is one standard deviation above the mean. Well, that is very nice for us and convenient. I'm going to draw a line up from each of those and try to be symmetric there, not perfectly. Do we know anything about the area or the percentage between one standard deviation of the mean in both directions? We do, don't we? It was 68%. We were told that. Okay, so that is a given. Whenever you are within or between one standard deviation of the mean for a normal distribution, then that tells you the answer is 68%. So 68% of all people who took the SAT math score would have had their scores between 400 and 600. So a significant majority there, okay? Definitely more than 2/3 of the people. So that is very important piece of information. Now, we were being kind to you because we gave you the numbers 400 and 600. We could have been more specific and given something like 350 and 550 or something like this. That would have required something like a z-score chart, okay? And since we're trying to just keep things general in this course, we're not going to go into that level of granularity or detail. You can wait for your statistics class for that. But you could do some things, like if I had said between 300 and 600, you could have used the fact that 300 is 2 standard deviations away and 600 is 1, and then used a little bit of arithmetic to solve. So you could be a little bit clever that way. Let's see if you can do the next one on your own here. Pause the video and try it. All right, let's see how you did. What's the probability or the percentage that someone has a math SAT score above 700, given that it's a normal distribution with an average of 500 and a standard deviation of 100? Okay, well 700 was how many standard deviations above the mean? It was exactly 2, right? Exactly 2. So what do we know about, using our previous slide, what do we know about 2 standard deviations away from the mean? Well, we know that if you are within 2 standard deviations of the mean, so that would be between 300 and 700, there's a certain percentage of values that lie within 2 standard deviations. Now notice what it didn't say. It didn't say less than 2 standard deviations or more than 2 standard deviations. It said within 2 standard deviations. So you have to be careful here to go to 300 because that's 2 standard deviations below, and 700, which is 2 standard deviations above. Within that range, if you will, what percentage of our values live there? If you said 95%, you would be correct. Okay, so what does that mean? Is our answer 95%? Do you have a 95% chance of getting a math score for SAT math above 700? No, that's a very high score. Highly unlikely, right? So hopefully that would tell you something's off if I'm thinking the answer is 95%. What would you need to do? A little bit of arithmetic, maybe? Let's think it through. If 95% is between, right, those two numbers of 300 and 700, that would mean that the rest of the percentage that adds up to 100% would be within the tails. And we'll talk more about tails if you take a formal statistics class, okay? So these tails right here, tails, tails, tails. These tails are symmetrical because we have a normal distribution, so they have to have the exact same value in each tail. So if we know that there's 100% of all values under the curve, and we've already confined 95% of them to be between a 300 and a 700, then what is left for those tails? If you said 100 minus 95 gives me 5%, you would be right. That's the total left in your two tails. But there's two of them, and they're symmetrical. So can you divide 5 by 2? I hope so. And you would get 2.5% here and 2.5% there. Now, maybe this is triggering something from what we just saw. If you're a visual person, you saw a picture a few minutes ago on the last slide, and it had 2.35% in those tails. And you're thinking, Professor, you lied to me. Nope, I didn't. Those two percentages and those two portions of the graph were not the entire tail. If you look very closely, there was a cutoff. Those were 3 standard deviations away from the mean, right? They were not the entire leftover amount after 2. So there was a little portion, right, tiny little portion beyond the third marker there. So keep that in mind. So 2.5% and 2.5% would be the percentages or the likelihood of either being below a 300 or above a 700. So the answer for the question, what is the percentage of people scoring above 700 for the math SAT? The answer would be this number here, 2.5%. So less than a 3% chance, less than 3% of the population of people who take the SAT math are going to achieve that result. Okay, so if someone is telling you they scored a 750, maybe you're around a genius, but probably not true. Okay, now let's take a look at the last one. See if you can do this on your own. Okay, so the last one says, what is the probability or the percentage that someone scores an SAT score for math below 300? Notice where 300 was. It was 2 standard deviations below 500, right, below the mean. So 2 standard deviations below. Well, we don't have to do much more work than last time because we already remembered that 95% of all values lie within 2 standard deviations of the mean, so between 300 and a score of 700. And here they're just asking me what percentage are below 300. We already know the answer from above, don't we? This is kind of an easy problem now. The answer is the same as last time. It's actually just as likely to score an SAT math score below 300 as it is above 700 because of the symmetry. So maybe you could tell the answer without doing any work by just looking above. The answer is 2.5%. Okay, so here we're just talking in this video today conceptually about what is a normal distribution, what is a bell curve, and what does that tell me about different types of values based on what I know about the mean and the standard deviation. To get into more granularity, you're going to have to take a statistics class, but hopefully this whets your appetite and makes you excited to study more about normal distributions in the future. All right, well, that's all for now. If you have any questions, please reach out to me. Otherwise, happy practicing, because math is not a spectator sport. I'll see you next time.